Section 3 is going to allow us to use molar mass to convert between grams and moles. Hopefully you feel confident about converting between moles and atoms or particles or ions, whatever, using Avogadro's number. Now you'll be able to convert between moles and grams. The molar mass is a useful conversion factor. It helps us to convert moles of a substance to grams or grams to moles. As long as we have our periodic table available to us, we can look, for example, to find silver, and we can say that 1 mole of silver has a mass of 107.9 grams. We can then make two conversion factors. We can have the mass on top per 1 mole, or we can say that 1 mole of silver has a mass of 107.9 grams. Let's look at a sample problem. Silver is used in the manufacture of tableware, mirrors, dental alloys, and jewelry. If the design for a piece of jewelry requires 0.750 moles of silver, how many grams of silver are needed? Well, we need to start with what I'm given. I'm given moles of silver. I want grams. So we got to set it up. What do I want? I want grams. What have I got? I've got moles. So we need to use our conversion factor that has the 1 mole of silver on the bottom so that moles of silver and moles of silver will cancel with the grams on top. 0.750 times 107.9. I started with 3 sig figs, so I need to round to 3 sig figs. I would need 80.9 grams of silver. Try it in your calculator to double check. Conversion factors are written for compounds in the same way as they are written for elements. We would say that 1 mole of sodium chloride has a mass of 58.44 grams of sodium chloride. We can write the conversion factors the same way. We can say that 1 mole of sodium chloride on the bottom is equal to 58.44 grams. And again, we found that by adding 1 Na and 1 Cl together. We can flip-flop that and say, well, 1 mole of NaCl has 58.44 grams. Let's do another sample problem. Let's say we have a box of salt that contains 73.7 grams of sodium chloride. How many moles are present? Well, let's use those conversion factors from the very last page. If I have grams, I need to get to moles. So what do I want? I want moles, so that needs to be my top unit. And what have I got? Well, like we said, we started 73.7 grams. I got to have my grams on the bottom. Those will cancel. So 73.7 times 1 divided by 58.44. We started with 3 sig figs. We're going to end with 3 sig figs. Make sure that you label your units. That would be moles of sodium chloride. Let's look at a sample problem where we convert between grams of a compound and grams of an element. We have a hot pack that consists of a bag of water and an inner bag that contains 10.2 grams of calcium chloride. How many grams of chlorine are in the 10.2 grams of calcium chloride in that inner bag? Here's a little background on heat packs. They're used to reduce muscle aches, inflammation, muscle spasms, and when that bag is smashed, the calcium chloride dissolves in the water and heat is released. What do we know? We know that we have 10.2 grams of calcium chloride. So we're going to go from grams of calcium chloride to moles of calcium chloride. Then look at our mole factor, see how many moles of chlorine are in that, and then go to grams of chlorine. This is going to take a few steps. So grams of calcium chloride, I need to have grams of calcium chloride on the bottom. So that means we need to look at the periodic table and add up 1 calcium and 2 chlorines to get that molar mass. That takes care of getting rid of grams of calcium chloride. But then I need to get rid of moles of calcium chloride. So I'm going to say 1 mole of calcium chloride down here on the bottom has 2 moles of chlorine. We just have to look at CaCl2 and go, oh, well, in 1 mole of calcium chloride, there's 2 chlorines. And then we look at the periodic table. To get rid of moles of chlorine, I got to say, well, 1 mole of chlorine has a mass of 35.45 grams. Now we multiply the whole top and the whole bottom, and we do top divided by bottom. So 10.2 times 2 times 35.45, all divided by 110.98. Again, we started with 3 significant figures. We need to end with 3 significant figures. We should get 6.52 grams of chlorine. This shows us a little summary of conversions. Moles is my central unit. If I know moles, I can get to mass, I can get to particles. If I know particles, I can only get to moles, and then I can get to mass. Same with mass. The only thing I can get to from mass is moles. Then I can go to particles, but moles is my central go-to. When we go from moles to particles, we have to use Avogadro's number, 6.022 times 10 to the 23rd. To go from moles to mass, we have to use the molar mass, and we look at the periodic table to figure out that molar mass. Take a minute to look over the learning goal to make sure you feel confident about this section. In this section, we are looking at mass percent composition. Given the formula of a compound, calculate the mass percent composition. Because the atoms of the elements in a compound are combined in a definite mole ratio, they are also combined in a definite proportion by mass. When we know the mass of an element in the mass of any sample of a compound, we can calculate its mass percent composition, or mass percent, which is the mass of an element divided by the total mass of the compound and then multiplied by 100. Mass percent composition of a compound can be calculated using molar mass. We just use the periodic table. The mass of each element is divided by the molar mass of the whole compound, and then we multiply by 100. Let's say the odor of pears is due to the organic compound propyl acetate, C5H10O2. What is the mass percent composition of propyl acetate? So we need to figure out what the whole compound weighs. So we need to add up 5 carbons, 10 H's, and 2 O's. Then, to find the mass percent composition for each element that's in that compound, we need to take the part and divide it by the whole. What are 5 carbons divided by the whole compound's mass and times it by 100? 10 H's divided by the whole mass, 2 O's divided by the whole mass. So here we go. We went from 5 moles of carbon, and we got rid of moles of carbon by looking at the periodic table. 1 mole of carbon has a mass of 12.01 grams. So those will cancel, leaving me that in this compound, 1 mole of this compound has 60.05 grams of carbon. We had 10 moles of H, so we got rid of moles of H and went to grams of H. And we had 2 moles of oxygen. We went to grams of oxygen. Then we added it all up to get the whole molar mass is 102.13 grams. Now that is what we will be dividing by. That's our whole. We're going to do now each of these parts and divide it by the whole. 60.05 grams of carbon divided by the whole times by 100. This compound is made up of 58.8% carbon. We'll do the same. 10 hydrogens mass is that 10.08 grams of hydrogen divided by the whole times by 100. This compound is made up of 9.870% hydrogen. And lastly, for the oxygen, there was 2 oxygens. 2 oxygens is 32 grams divided by the whole, 31.33% oxygen. And then notice, if I were to add up all of these percentages, they should equal 100%. I encourage you to pause the video real quick so you can find the percent of nitrogen in each of these different types of fertilizers. So I have NH3. Find the whole mass of NH3 and then just do the 1 nitrogen divided by the whole mass times it by 100 to figure out the percent of nitrogen in NH3. Same with this one is ammonium nitrate. There are 2 nitrogens in this compound, but we need to find the whole mass as well of 1 nitrogen, 4 H's, another nitrogen, and 3 O's. Same with, let's find out the percentage of nitrogen in this compound and the percentage of nitrogen in this last one, ammonium sulfate. Take a minute and see if your answers match these. The numbers on a package of fertilizer give the percentages of each nitrogen, phosphorus, and potassium by mass. If you've ever noticed that. Again, take a minute now and look at the learning goal. See if you feel comfortable with these learning goals.